Okay, so sorry you can't see me, but my video making software is giving me fits today. So you're just going to be able to hear my voice and see my hand. Hello. So we're going to do a couple of videos for you to reference while I'm away. And the first one is going to be covering simplifying radicals. So I'm not going to write the date on these. But I will write the titles. So simplifying radicals. So this is the video intended for Wednesday, but if you write it ahead of time, that's totally fine. Okay, so when we talk about radicals, we mentioned before that radicals undoes exponents, right? Or undoes repeated multiplication. So I'm going to go ahead and write that. Radicals undo repeated multiplication. Okay, so our example that we talked about in the last class was if we do something like 5 times 5, we know that's 25, right? Or we could write this as 5 squared equals 25. So to undo a square, we can use a square root. So in other words, this is the same thing as saying if I take the square root of 25, that equals 5. And the reason that that is because a square root, my little index number here is a 2, right? So if I take the square root of something that has 2 copies of a number below it, then the square root and the square actually cancel one another out, right? These undo one another, and I'm left with just 5. So when we're dealing with square roots, the goal here is really to have 2 copies of a number under a square root. Because if we have 2 copies, then we know that that squared, or that second copy, right, cancels out the radical, and we're left with just the number itself. So a couple other examples. If I have something like the square root of 81, right? 81 is the same as 9 times 9. Right? So we could write this as the square root of 9 squared. And then we know that a square and a square root cancel each other out. So this would just leave us with 9. Okay. And I'm sorry, it's like refocusing every time I move my hand. I'll try to keep my hand out of there as often as possible so it's not giving us fits. But we may just have to struggle through it on this one. All right. So one way to think about it, and this is how they're probably going to describe it on Knewton, is in this sense right here, where we want to write the number under the radical as something squared, or find factors that are squared, because then we know if we have a square under a square root, we can bring that factor out. The way that I'm going to describe it is a little bit different, hopefully helpful. So what we're going to look for is 2 copies of a number. So I'm going to show it as if you're factoring out the number like this, 9 times 9. And then since we have 2 copies of a 9, that tells me that I can bring the 9 out. And notice we don't have any other factors. 81 is exactly 9 times 9. So that's all. It just equals 9, and there's nothing under the radical. Okay, same thing if I had like square root of 100. Okay, I could factor 100 down. 100 is 10 times 10, right? So just like the last example, I could go ahead and write this as the square root of 10 squared, and then my square and my square root are going to cancel one another, and this just gives me 10. Okay? Or I could see, hey, there's 2 copies of a 10. If there's 2 copies of a 10, I can take that 10 out. Now the difference here is some people don't know right away that 100 is 10 times 10, and that's totally fine. So they can actually factor it down further. So let's assume for just a second that maybe you saw 100 and you weren't thinking 10 times 10. Maybe you thought 2 times 50, right? So the good news about doing it this way is I could say, okay, I'm trying to simplify the square root of 100, and I know 100 is 2 times 50. Well, I don't have 2 copies of a number here, right? So I need to keep going. Well, I know that 50 is 2 times 25. right? And 25 is the same as 5 times 5. And then I can't go any further because 2, 2, 5, and 5 don't simplify any further. But what's helpful about doing it this way is I can now write this in a couple of different ways. I could go ahead and write this as this is the same as 2 squared times 5 squared, right? Because I have two copies of a 2 here, and I have 2 copies of a 5. So if I have 2 copies of each, then I can see that I can write it this way, and then the square and the copies are going to cancel. So this just gives me 2 times 5, which is still 10. Or if you don't want to write all this out, you can just look at the number of copies. So I have 2 copies of a 5, so I can pull out a 5. I have 2 copies of a 2, so I can pull out a 2. And whatever I pull out, I multiply together. So 2 times 5 gives me 10. So you can see, regardless of which method you use, you should get the same answer. Okay, but whenever I start explaining how to simplify radicals, I'm going to show this method of looking for the number of copies we need in order to pull something out of a radical. Okay, so for this section, I'm pretty sure all we deal with is square roots. So I'm just going to put a little note off to the side here and just say, so for square roots, any number that you have 2 copies of comes out of the radical. Okay, so if we're simplifying square roots, all we have to do is figure out what do we have 2 copies of. And if we have 2 copies of it, then we can pull that number out. Right? If we don't have 2 copies of it, then it actually has to stay under the radical. So that's what we're going to look at next. All these examples were perfect squares. So I'm going to look at some that are not perfect squares, right? So let's say, but what about ones that look like the square root of 392? Right? Off the top of our head, we may not know what the square root of 392 is. That's not an ideal number to work with. So if we don't know if it's a perfect square right away, I'm going to go ahead and just start prime factoring it down to try to figure out if I have any common factors in here. So I see that it ends in 2. If it ends in 2, that means it's an even number, and we know all even numbers are divisible by 2. So I'm just going to do 392 divided by 2, which gives me 196. Now again, 196, I don't know any factors off the top of my head, but again, it ends in a 6, so I know it's even, so I know 2 goes into it again, which leaves me with 98. So our numbers are getting smaller, but again, 98 is not a number that I know any 2 factors of off the top of my head. So I'm going to go ahead and divide it by 2 again, because it ends in 8, so I know it's even. 98 divided by 2 gives me 49. And 49, I actually know some things that I can multiply to get 49. 49 is 7 times 7. So now that I have it completely factored out with all these little factors, I'm just going to look and see, do I have 2 copies of anything? Well, I can see that I have 2 copies of a 7, so that's good. That means I can bring out a 7, right? And then I notice I have 2 copies of a 2, so I know I can bring out a 2. But I have this other 2 that's left over. So if I have something that's left over, it has to stay under the radical because it didn't have enough copies to come out. So what we're doing here is we can write this one of 2 ways. We can go ahead and say, oh, this is the same thing as 2 times 2 squared times 7 squared. And then the things that I have 2 copies of can come out. So I can write this as 2 times 7 and have a 2 underneath. Or I can just go straight from here and say I'm bringing out a 2, and then I'm bringing out a 7. Whatever you bring out, you multiply together. And then what I'm left with under the radical is a 2. Okay, so you do not have to write this step unless that helps you out. Okay, I'm probably going to stop writing this step here in a few examples and just go straight to this. Now, once we get to this step, we do need to go ahead and multiply these numbers together. So this gives me 14 square root of 2. You know, and same thing, if we would have simplified it up here, we would still get 14 square root of 2. Okay. So let's look at another example, same idea of one that doesn't simplify perfectly. Move my paper back down here. Let's look at the square root of 40 x to the 10th y to the 3rd. So this one's a little bit different, right? Because we have variables, but we're not going to freak out. We're just going to ignore them for right now. We're going to focus on the 40. We know 40 is not a perfect square, so we're going to go ahead and prime factor it. 40 is 4 times 10, right? And then the 4 I can break down. 4 is 2 times 2, and 10 is 2 times 5, right? So notice I only have 2 copies of a 2. So that tells me I can bring a 2 out. So I'm going to go ahead and write over here. I know I can bring a 2 out, but I'm going to be left with this 2 and this 5, right? They didn't have 2 copies, so they're going to have to stay underneath the radical. So you can write under the radical that you're bringing out a 2 and that you're leaving in a 2 and a 5, or we can just multiply those back together. So underneath our radical, we know that we still have a 2 and a 5, or you can go ahead and just write that as 10. Okay. Now we want to look at our variables. If we look at our variables, we have 10 x's, right? X to the 10th power and y to the 3rd. So I'm going to write that out so you can see it visually, and then I'll show you a shortcut. So we basically have 10 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 3 y's. Y, y, y. So when we think about how many we have, we're going to use the same idea that we need 2 copies in order to bring out one of that factor. So if I have 10 x's, for every 2 x's, I can bring out an x, right? So for those 2, I can bring out an x. For these 2, I can bring out an x. For these 2, I can bring out an x. For these 2, I can bring out an x. And for the last 2, I can bring out an x, right? So really what we're doing is we're saying, if I have 10 x's, how many groupings of 2 can I come up with, right? And the answer to that is 5. So we're actually pulling out an x to the 5th, because here I'm bringing out an x, an x, an x, an x, an x, which is 5 copies of an x. So I'm actually pulling out an x to the 5th power. Okay, and notice that took all my x's. I don't have any x's left over. Now when I look at my y's, I can take out a y for this first pairing of 2 y's, but I don't have another pairing of 2 y's, right? So that means I can bring one y out, because I had 2 copies, and then one y is going to be stuck still underneath the radical. So I'm bringing out a y, and I'm left with a y underneath. And then I just simplify. So this leaves me with 2x to the 5th y square root of 10. Okay. So that we don't have to write out all of our copies, I want to show you a little shortcut. Because what if this was like x to the 100th, right? We don't want to write out 100 x's and then do a bunch of little circles circling 2. So what we're really saying here is if we have 10 x's, how many pairings of 2 can we have? We're really just doing 10 divided by 2, right? There's 10 x's. For every 2 I can bring out an x. So 10 divided by 2 is 5, which means I can pull out 5 x's. So the shortcut here, I'm just going to write shortcut, is that we can just divide the exponents. Okay? So in other words, if I'm looking at this problem I just did, I'm just going to ignore the 40. If I am looking at the square root, right, and I'm going to go ahead and write the 2 in there just so we see the number, the square root of x to the 10th, y to the 3rd, if I look at the x's, I can just divide these 2 numbers, right? I can say 2 goes into 10 how many times? Well, it goes in 5 times. 5 times 2 is 10, and we're not left with any remainder, right? So this is how many x's you can bring out, and your remainder is how many are left under the radical. So notice here we brought out an x to the 5th, and there was no x's underneath, right? Oops, I forgot my y. Sorry, forgot my y. The same thing with the y's. If I want to use a shortcut here, I want to know how many copies of 2 do I have within 3. So I can just say, well, 2 goes into 3 how many times? Well, it goes in 1 time, and that leaves me with a remainder of 1, right? So that means I can bring 1 y out, and I have 1 y left over. Okay, so this is a really helpful shortcut so that we don't have to write out all the copies of x and all the copies of y every time we work through one of these problems. So let's look at a few more examples just to give you an idea of the types of problems you're going to see in your homework. Okay, so scooting this up here. Excuse me. So I'm just going to say more examples. More examples. The square root of 72. Okay, so here we don't have a variable. 72 is not a perfect square, so what we're looking for is, do I have 2 copies of any factor within 72? So I'm going to just go ahead and start factoring 72. I know it's even, so I know 2 has to go into it, right? 2 goes into it, what, 36 times? And 36, that's even, so 2 goes into 36 18 times, right? 18 is 2 times 9, and 9 is 3 times 3. So now that we have it completely prime factored here, I can just look, do I have 2 copies of any given factor? Well, I have 2 3s, so I can bring out a 3. I have 2 2s, so I can bring out a 2, and then I'm left with this other 2. So what that tells me is that I'm bringing out a 2, I'm bringing out a 3, and I'm left with a 2 underneath. So when I simplify this, this just gives me 6 square root of 2. Okay. So hopefully the ones with just numbers won't give us too many fits. Another thing they might throw at you is something like this, the square root of 25 minus 9. Now, when we look at this, 25 and 9 are actually both perfect squares. But we don't have any rules for simplifying these individually under a square root. That's not, we can't just say this is going to be the square root of 25 is 5, the square root of 9 is 3, and 5 minus 3 is 2. It doesn't work that way. We have to simplify what's underneath here because of order of operation, right? Order of operation tells us to do parentheses first or any kind of grouping symbol. And here the square root is a grouping symbol. So we have to simplify this first. 25 minus 9 is 16. And the square root of 16 is 4, right? If we're not familiar with that, you can prime factor this out. You could say this is 2 times 8. 8 is 2 times 4. 4 is 2 times 2, right? We can bring out a 2 here, can bring out a 2 here, and 2 times 2 gives us 4. Okay. So whatever your method is, you should get the same answer no matter what. And I'm really sorry that this video keeps doing this refocusing every 2 seconds. Hopefully you're not getting dizzy or ridiculous. All right, so I want to do 2 more examples, and then I'm going to give y'all some to work, okay? So next example is going to be the square root of 50 x squared y to the 3rd z. Excuse me. All right, so we're going to look at the number first and not worry about the variables. So if I look at just the number, 50 is the same as 2 times 25, and 25 is 5 times 5. So what this tells me is that I can bring out a 5, and I'm going to be left with a 2, right? So I'm going to go ahead and hold off on writing anything at this point, and I'm going to look at my variables. Okay, remember my shortcut with my variables is I take this index number, which here we're dealing with a square root, so this is a 2, and I'm going to see how many variables can I bring out? How many copies of 2 do I have in x squared, right? How many copies of 2 do I have in y to the 3rd? And how many copies of 2 do I have in z? Okay, so I'm just going to write them out to the side. And if you don't have to show this much work when you're doing your homework, that's totally fine. But I just want to make sure we understand as we're learning. So if I look at just my x's, my exponent on my x is a 2. And I want to know how many copies of 2 do I have within 2. So I just do 2 goes into 2 how many times? 1, right? 1 times 2 is 2. And I'm left with no remainders. So this is how many x's I can take out. And this is how many x's I'm going to be left with. So I'm taking one x out because 2 goes into 2 one time. And it goes in evenly. I have no remainder. So I have no x's that should be left under this radical. Then I do the same thing with the y's, right? Y's, I want to know how many times does 2 go into 3. So I go 2 goes into 3 one time, right? 1 times 2 is 2. And notice I have a leftover. So this means I can take one y out, and I'm going to be left with one y left. Right? I have one left over, so it's going to be stuck under the radical. And then if I look at my z's, I only have one z. So I want to know, does 2 go into 1? Well, no. If I only have one z, I'm not going to have 2 copies. So that doesn't go in at all, right? So I'm going to be left with that one z still under my radical. So no z's out, one z left. Okay. All right, so let's write what we came up with. So basically, the things we're taking out this 5 that I circled, so let's write that. Then we're taking out one x and one y. So x, y. And then underneath our radical, number-wise, we're left with this 2. And letter-wise, remember we had no x's left over. We had one y and we had one z. So we have y, z still underneath. Okay. Does it kind of make sense? Hopefully. All right, let's look at another one. Let's look at the square root of 63 x to the third, y to the fourth. Okay, so same idea. I'm going to do my numbers and my variables separately and figure out how many copies of 2 do I have of my numbers and my variables. So when I look at this one, looking at numbers first, it's not even, so I know it's not divisible by 2, but I know both these numbers are divisible by 3. So 3 goes into 63 21 times. 3 goes into 21 7 times, and 7's prime. So the only thing I have 2 copies of is 3. So that tells me I can take out a 3, and I'm going to be left with a 7, right? So then I want to look at my variables. For my x's, I have 3 x's, right? And this is a square root. So if it's a square root, I need copies of 2. So how many times does 2 go into 3? 2 goes into 3 one time. 2 times 1 is 2. And it's going to leave me with one remainder. So I can take one x out, and I have one x left, right? And then let's look at our y's. Our y's, we have 4 of them. I want to know how many copies of 2 can I get out of 4. So 2 goes into 4 2 times, right? 2 times 2 is 4, which means I have no leftovers. So I can take 2 y's out, and I have 0 left. So when I put all this together, right, what am I taking out? Well, number-wise, I'm taking out a 3. So I'm going to go ahead and write a 3. Letter-wise, I can take out one x, and I can take out 2 y's. So I have x and y squared. And then what's left over underneath my radical, number-wise, I have this 7 that's left over. My x's, I had 1 left, and my y's, I had no left over. So I just have 1 x left over under that radical next to the 7. Okay. All right, so that is pretty much the extent for right now of the types of problems that you're going to see. I'm going to give you 3 problems to practice. So just pause this video and work out those 3 problems, and then play it again, and you can see the solutions to them. And then I'm going to do a few more examples after that. So don't stop the video now, because you will not have seen all the problem types that are in your homework. So here's our practice problems. All right, so you can go ahead and pause the video and work these out. And then when you think you've got them, go ahead and hit play again, and you can see me work them out and talk about them. All right, so here's the 3 worked out. You can check your answers. I'm going to go ahead and talk through each of them just really quickly. On the first one, square root of 48. I notice I have a 4 and an 8, right? So I know right away this is divisible by 4. If you broke it down further and divided by 2's, you should still get the same thing, okay? So I said 4 is 4 times 12. 12 is 4 times 3. And then I had 2 copies of a 4 and a 3 left over. So 3 stays under the radical, 4 comes out because I have 2 copies of it. On the second one, I have variables on this one as well. Now the number part was super easy, right? Because 49 is a perfect square, 7 times 7. So I know I have a 7 that comes out. And then I look at my variables. This is a square root, which means I need 2 copies. So I want to know how many times does 2 go into that exponent. So 2 goes into 3 one time with 1 left over, right? So that means I can bring out 1x. So you can see here I brought out my 1x, and my 1 that's left over stays under the radical. Then I do my y's. How many times does my index here, my square root 2, go into my exponent 6? Well, 2 goes into 6 3 times. So that means I can take out 3 y's. So that gives me a y cubed out here. And it goes in evenly, so I have no leftovers. So if I have no leftovers, there's no y's left underneath. Okay. I will go ahead and mention here, when you're working through your homework, I'm not going to require that you write this out. If you do it in your head, that's totally fine. On a test, it may help you get some extra credit if you miss a problem and I can see your thought process. But for the most part, if you can just say, okay, well, 2 goes into 3 one time with 1 left over, so I'm pulling out 1 and I have 1 left, I'm okay with that. I'm not going to mark off for you having not written this stuff, okay? All right, on the last one, 125 is divisible by 5. 5 goes into it 25 times, and 25 is 5 times 5. So since that has 2 copies of a 5, I can go ahead and pull out a 5, and I'm going to have a 5 left over under my radical. So you can see in my answer down here, I brought out a 5, 5 left over. Then I look at my x's. Now, if there's no exponent written here on the x, that's an implied 1, right? So I want to know, how many times does 2 go into 1? Well, 2 doesn't go into 1, right? It goes in 0 times. So that means I can't bring any x's out, but I will have 1x left over still in my radical. Okay. And then I look at my y's. Y's, I have 4 of them. How many times does 2 go into 4? If you need to do long division, you can do it. 2 goes into 4 2 times, so I can bring out 2 y's. That's why I have a y squared here. And 2 goes into 4 evenly. There's no leftovers. So if there's no leftovers, then there's no y's underneath your radical here. Okay. And then we look at our z's. Z's, we have 5 of them. 2 goes into 5 2 times, so I can bring out 2 z's, or z squared. And I'm left with 1, so I have 1 z left in the radical. Okay. All right, so those were the practice problems. What I want to show you now are just 3 more examples of kind of a little bit more difficult problem, but it's really the same idea. And actually, they may not be more difficult. We'll see. We'll see what your take is on. You can tell me when I get back if you thought it was worse. Okay? All right, so I'm just going to call this more complex examples. All right. So the first one is the square root of 245 x to the 22nd power y to the 16th all over the square root of 5 x to the 8th y to the 6th. So even though this looks relatively horrible, it's kind of not, because we have a rule that says if we have a square root on the top of the fraction and we have a square root on the bottom of the fraction, we can actually write this whole thing as just the fraction with one big square root around it. So that's what I'm going to do. I'm just going to write this under one huge square root. So 245 x to the 22nd y to the 16th all over 5x to the 8th y to the 6th. Right? So not too bad. Not too bad now, because if this radical wasn't here, This is exactly the type of problem we did in the exponent section, right? Like advanced properties of exponents and that type of thing. We've done this. We've seen this. So all we have to do is simplify this first, right? We can go ahead and reduce the number part because 245 divided by 5 is what? I don't know. Get your calculator. 245 divided by 5 ends up being 49. Comes out nicely. Okay. And then we can also simplify these x's, right? Because we have the quotient rule. The quotient rule says if I have the same base on top and bottom, I can just subtract the exponent. So this is like doing x to the 22nd minus 8. X to the 22nd minus 8 gives me x to the 14th. Okay? And then I do the same thing with the y's here. I have y's on top and bottom, so I can use product rule. This would be like y to the 16th. And then if I want to move this 6 up, right, I subtract it. Y to the 16th minus 6 leaves me with just y to the 10th. And now this is actually a really easy problem that we can simplify. Probably easier than the last practice problems we just did, right? So 49 is a perfect square. This is 7 times 7. So that tells me I can bring out a 7. And I don't have any numbers left over. And then x and y, those are also perfect squares here because this is a square root. How many times does 2 go into 14? Well, 2 goes into 14 7 times. So that means I can bring out an x to the 7th. And I don't have any remainder. So if I have no remainder, I have nothing left under the radical. Same thing with the y. 2 goes into 10 5 times. So that means I can bring out a y to the 5th. Since 2 goes into 10 evenly, I have no remainder, there's nothing left under my radical. So I don't even have a radical in my answer. Not too bad, right? All right, so let me look at a couple more. I want to look at another one. Let me look at another one like this, and then I'll show you how we can use this rule backwards. So what if we have the square root of 300 x to the 28th y to the 28th all over the square root of 3x to the 14th y to the 12th. Okay. Same idea here. I have a radical, a square root on top, and a square root on bottom. So instead of doing those square roots individually, I can just move the square root out over the whole problem. And write this is 300x to the 28th y to the 28th all over 3x to the 14th y to the 12th. And once I have it written all under one radical, I can go ahead and just reduce it, right? If I do 300 divided by 3, that gives me 100. Excuse me. If I look at my x's, I have x to the 28th on top and to the 14th on the bottom. So it'd be like x to the 28th minus 14, which gives me x to the 14th. And then when I look at my y's, same thing. I have y to the 28th on top and 12th on bottom. So it's like subtracting those exponents, which gives me y to the 16th. And now this is something I can easily simplify because it's a perfect square, right? The square root of 100 is 10. The square root of x to the 14th, again, we just use our little shortcut. Our index 2 goes into 14 7 times, so I can bring out an x to the 7th. 2 goes into 16 8 times, so I bring out a y to the 8th. There's no leftovers, so there's no radical. All right, let me look at one more, and then I will give y'all some to practice, and then that's the end of this lesson, okay? So last example here, let's look at one that's already in one big square root. Let's look at 49 x to the 26th over 36 y to the 14th. So notice this one's already written as one big square root with a fraction under it. But if you notice, I cannot simplify 49 over 36. Those don't have common factors. And I can't combine my x and my y's. Obviously, they have different bases. So in this case, what I'm going to do is I'm actually going to separate them. 49x to the 26th on top, and 36y to the 14th on bottom. So in this case, it didn't help me to have it all together because I can't simplify. So I'm going to break it up into two separate radicals and then just simplify them individually. So if I simplify the top, square root of 49 is 7. Square root of x to the 26th, again, this is a square root, so 2 goes into 26 13 times, which means I can bring out an x to the 13th. No leftovers, so no radical. On bottom, the square root of 36 is 6. And the square root of y to the 14th, well, again, square root. 2 goes into 14 7 times, so I can bring out a y to the 7th with no leftovers. So we're just going to leave it like that. Not too shabby, right? So the rule, basically, what we can take away from this last part on these more complicated examples is if you have problems like these first two where there's common variables or numbers on top and bottom, then you want to go ahead and just write it as one big square root so you can simplify down to something easy that you can go ahead and work out. If you start off with one big one that you can't combine, then separate it into two little ones that you can simplify. Okay, so I'm going to give y'all 3 practice problems. Here we go. All right, so here are your practice problems. Go ahead and pause the video so that you can write these down and work them out. And then when you're ready to check yourself, go ahead and play the video and we'll talk about them. Okay, so we're going to go ahead and talk through them. On the first one, notice it's written as one big square root, but there's nothing to combine or simplify under this square root. So I'm going to go ahead and break this one up into 2 separate radicals on top and bottom, and then just simplify them individually. So 4x to the 10th becomes 2x to the 5th. On bottom, square root of 169 y to the 8th becomes 13 y to the 4th. Okay. On number 2, this is just kind of a review of the ones we did before. Simplified basic stuff here. So square root of 16 is 4. Now square root of x to the 3rd, here my little square, my 2 doesn't go into 3 evenly. 2 goes into 3 one time, which means I can take 1 out with 1 left over. So I can bring out an x, and underneath my radical, I still have an x. Okay, y to the 6th, 2 goes into 6 3 times, so I can bring out a y cubed. Okay, and then on number 3, this one's actually written separately, but as you can see, we have x's and y's on top and bottom, and I know that 12 is divisible by 3. So I'm going to go ahead and write the separated radical as one radical over the whole fraction. And then once I have it written all together, then I can go ahead and simplify. 12 divided by 3 gives me 4. I can combine my x's by subtracting their exponents, which gives me x to the 28th. And then I can combine my y's by subtracting their exponents, which leaves me with y to the 10th. And then I just simplify. The square root of 4x to the 28th y to the 10th becomes 2x to the 14th y to the 5th. Okay, so we're going to leave it off. We're just going to go ahead and stop right there. That's the end of simplifying radicals. If you watch this video on your own, good job. Go ahead and start your homework. If you are watching this video during class time, if you have any questions, feel free to ask Brittany. She would love to come over and explain more in depth to you if you have a misunderstanding on any of it. All right?